Welcome to Lecture 25, in which we will move into Chapter 6 for the first time. Chapter 6 in your textbook is entitled Quantum Versions of Classical Computations. And in this chapter, we're going to be looking at classical circuits and how to make these classical circuits reversible, which means that you can recover the input bits from your output. For instance, if we had an inverter, you know that you can always recover the input to the inverter by simply inverting the output again. In other words, let's to use the symbols that most of you will be familiar with. You know that if we input Boolean variable x into this inverter, then we will, of course, get the complement of x, which I'll denote by x prime. And now, if we wanted to know how to recover the input to the inverter, of course, we would just take that output and put it in another inverter, and we could get x again. But notice that, let's say that we take the usual NAND gate. You have x and y, and then the output would be the NAND of x and y, or in other words, xy complemented. Well, simply from that one value, xy complemented, you cannot figure out what x and y separately were. So we'll say this first case is reversible, but the second one is not reversible. And most of the operations that you're familiar with on classical bits are not reversible. The NAND is not reversible, AND is not reversible, NOR is not reversible, OR is not reversible, exclusive OR is not reversible. So most of the ones that you're familiar with are not reversible. And one of the things that we want to talk about in this chapter is how to get reversible versions of the classical gates, and then to find quantum analogs to these, because that will, once we get reversible versions of the classical gates, then it will be easy for us to implement classical circuits in the quantum realm. So that gives you just a very brief idea of some of the ideas that we'll be talking about in this chapter. And now, to be more specific, the first thing that we'll consider in more detail is the Toffoli Gate. Let me make sure I spelled this correctly. Okay, there's two F's. So the Toffoli Gate. And the Toffoli Gate works on 3 bits, and it will go like this. Now, this is the symbol that your book uses for the Toffoli Gate. And I we'll suppose that the input bits are A, B, and C. And the first thing I want to call to your attention is, again, this is the symbol that your book uses for the Toffoli Gate. And the way that it's supposed to work is that that first bit A will remain unchanged, the first bit B will remain unchanged, and the last bit will be C, unless A and B are both 1. And in that case, when A and B are both equal to 1, then the last bit will be inverted, and so we'll get C prime. Now, again, to be consistent with the notation that we've been using most recently, I'm going to shade in both of these circles, but keep in mind that this is the notation that your book uses. But again, as I said, we'll go ahead and shade this in to be consistent with what we've been doing in recent lectures. So let's go ahead now and look at the truth table for the Toffoli Gate and make sure we understand everything about it. So we have A, B, C, and then I'm going to call this this third bit, I'll call it well, let's see, let me think about this for a moment. Okay, let's think about it this way. We'll have A, B, and C. Those refer to our input variables, and then we'll have T of A, B, C, and that will be the three output variables. But I won't write them as three separate things. I'll just write them as one triplet of bits. Okay, so obviously our possibilities here will be like that. And we've already said that the first two bits are always going to be the same. So we can go ahead and put AB. Well, let me go ahead and put the numbers. Well, yeah, I'm sorry. So we'll have A, B, 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 and A, B. Now, please understand that when I write down A, B here, actually I'll do it like this, just to make sure it's clear. So this is going to be a triplet. We're giving all three of the outputs. So the first output will always be equal to the first input. The second output will always be equal to the second input. But what about the third one? Well, it will always be equal to the third input, except in the last case when A and B are both equal to 1, and then in that case it will be equal to C prime. Okay, so this is what we have for all of the different cases. Now let's look at this in a little more detail. Let's look at a few examples. First of all, let's ask this: what is T of B1, B0, 0? So in other words, we're going to let A equal B1, capital A is equal to B1, capital B is equal to B0, and C is equal to 0. Well, the answer to this is that it will be equal to B1, B0, and 0, except when B1 and B0 are both 1, in which case it will be B1, B0, 1. Now let's think about that for a moment. The last, we're saying that the output, and we're concentrating now specifically on this third output. The third output is always 0, except when B1 and B0 are both 1, and in that case, it will be equal to 1. Well, if you think about that for a moment, then that means that we could say T1 of B1, B0, 0 is equal to B1, B0, B1 ANDed with B0. Because B1 ANDed with B0 is always going to be 0, except when B1 and B0 are both 1, and in that case, then it will be equal to 1. Okay. So this is our first observation. And notice that this gives us then a reversible AND gate. But why do I say that it's reversible? Because the first two parts of our output, B1 and B0, give us exactly the first two bits of our input, and the third one, let's see how we could say that. Wait just one moment here. Let's see. Okay, let's just try to construct this inverse of T of B1, B0, 0. And I believe that we'll find that we can do this in every case. So we have 0, 0, 0, 0, 0, 1. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So the idea now is that we're supposing that these numbers over here, these bits, represent the output of a Toffoli gate, and we're trying to figure out, is that enough information for us to get what the input was? Well, we know in every case that the way the Toffoli gate works, that the first two outputs are equal to the first two inputs. So we can certainly say that this 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, and 1, 1. We can certainly say that. Now, can we figure out what C was in each case? Well, remember that in every case that the third input will go through to the third output directly, except in the 1, 1 case. So we also know what the third input is in the first 7 of these cases. 0, 1, 0, 1, 0, 1, 0. And now in the case when, oh, wait. We don't want to include that last one because that's also a 1, 1 case. So now, the last two cases are the only two where A and B are both equal to 1. And so can we say what C was in each one of those cases? And I think the answer is yes, because in this first one, when the first two inputs are 1, remember it's going to invert the third one. So if the output was 0, the input must have been 1. And if the output is 1, the input must have been 0. So this is indeed a reversible situation. We can figure out the inverse of the Toffoli gate, and that will be true for all the cases that we're going to consider. Since this applies to the Toffoli gate in general, let me change this argument here to A, B, and C. And so if you wish, instead of saying input 1, input 2, and input 3, you could say A, B, and C. And again, we have figured out A, B, and C from T of A, B, and C. So over here, these three represent T of A, B, and C. And so the fact, one more time, the fact that we're able to figure out A, B, and C from T of A, B, and C indicates that the Toffoli gate is reversible. And so our first observation after that, after seeing that, is that if we have this B1, B0, 0 is our inputs to the Toffoli gate, then we get B1 and B0 as our first two outputs, and the third output will be B1 ANDed with B0. So this is a reversible AND gate. Let's look at some other examples. Let's suppose that we take other examples, and here I'll just say reversible AND. So on the other hand, if we take T of 1, 1x, we will get 1, 1x prime. And so this is one way to have a reversible inverter. Of course, the classical inverter, as we've already said, the classical inverter is already reversible. T of x, y, 0. Well, that's exactly what we've already seen. above, but we just called it B1 and B0. So that will be X, Y, X, ended with Y. What about T of 1X, Y? What does that equal to? Well, let's think about this one. So we have obviously the first two outputs will be 1 and X, but what will we get as our third output? Well, let's think about this for just a second. We could have let's say 1X, Y. One, of course, is always equal to 1. And so we can have 0, 0, 0, 1, 1, 0, and 1, 1. And now what will our output be? I'll say maybe first output second output, third output. And the third output is the one that will be of real interest, because we know that the first output will always be 1, since the first input is 1, and the second output will be 0, 0, 1, 1. And then what about that third output? Well, for the first two cases, it will just be equal to Y, so we have 0, 1. But in the last two cases, since the first input and the X input are both equal to 1, then the third input is going to get inverted. So this 0 will become a 1, and the 1 here will become a 0. And so now if you just look at this third output and compare it to what we have over here, we notice that it's equal to 0 when X and Y are both 0. It's equal to 1 when X is 0 and Y is 1. It's also equal to 1 when X is 1 and Y is 0. But it's equal to 0 when X and Y are both 1. And that probably looks familiar to you. That is X exclusive or Y. And for those of you who perhaps are not familiar with the exclusive OR function, is defined in this way. That is equal to X, Y prime, or X prime, X, Y prime, or X prime, Y. And it can be summarized, its fact is summarized in the following simple way. When X and Y have the same value, the exclusive OR of X and Y is equal to 0, but when they have different values, then the exclusive OR is equal to 1. So again, looking up here, in the first row, X and Y are the same, and so we get 0. And the last row, X and Y are the same, and we get 0. But in the middle two rows, X and Y differ, and there we get 1. So that's why this third bit is the exclusive OR of X and Y. And now let's look at another example. I'll skip down a little bit. Perhaps let's now look at T of X, Y, 1. What will that be equal to? Well, we know that the first one will be X. We know that the second will be Y. But what about the last one? Well, again, let's just take the approach of looking at the truth table. I think that's the easiest way to figure this out. So we have X, Y, and 1. Those are our inputs. And then we'll say first output second output, and then third output. Okay, the 1, of course, is always equal to 1. And now we look at the 4 combinations of X and Y. And of course, we know immediately what the first 2 outputs will be: 0, 0, 0, 1, 1, 0, 1, 1. And the last output will always be equal to the last input, except in the last case, and then it will be equal to the inverse of it, so we get 0. And so now think about this. Just look at X and Y, look at the first 2 columns, and look at this last column. Is equal to 1 in all cases except when X and Y are both 1, in which case is equal to 0. And so what is this equal to? This is the NAND. Of X and Y. Again, remember that the NAND is just the inverse of the and so if we AND X and Y together and then invert it, you can see that if either one of these is 0, we will get a 0, and then when we AND it, and then when we invert, we'll get 1. So this will always be equal to 1 if either one of these is 0, or if both are 0, we'll get a 1. The only time we will get a 0 is when both of these are equal to 1, and so that it looks exactly like this function right here. So we see that the Toffoli gate, at a minimum, will give us a reversible way to implement inversion, a reversible way to AND 2 bits, a reversible way to XOR 2 bits, and a reversible way to NAND 2 bits. Let's look now at an example of the use of Toffoli gates in a more complicated circuit. I'm not going to tell you right now exactly what this circuit is supposed to accomplish. Instead, what we'll do is try to figure this out ourselves, and then we'll know what this is. And by the way, this example is in your book. So here we have the circuit under consideration. The top line is C, the second one is X, the next one is Y, and the bottom 2 lines for the input have zeros. And you can see that the top 3 lines for the output will be CX and Y, matching CX and Y for the input. But the last 2 outputs will be named S and C prime. And you can see that over here on the right, I've put a truth table. And we want to figure out what S and C prime will be under each of these 8 possible combinations of values of C and X and Y. And notice that the first 3 gates we have here are Toffoli gates, and then the last 3 gates are controlled NOT gates. And by the way, we could get a controlled NOT gate from a Toffoli gate, so we could do this with simply all Toffoli gates if we wished. Okay, well, let's try to now figure out what S and C prime will be in this case. And S is determined simply by controlled NOT gates. C prime is determined all of this by Toffoli Gate. So let's start with the one that will be simpler, which is S. When C and X and Y are all 0, then you notice that this is connected to the C line, this is connected to X, and this is connected to Y. So when C and X and Y are all 0, then S does not get inverted at all, and it's equal to 0. When C and X are both 0, but Y is equal to 1, well, the fact that Y is equal to 1 will have cause an inversion here, but since C and X are both 0, there will be no inversions here or here. So we have this 0 gets inverted one time, and so S is equal to 1. Likewise, for the next line, if X is equal to 1, but C and Y are 0, then the fact that C is 0 and Y is 0 means that neither one of these will cause an inversion, but the fact that X is equal to 1 means that this will invert. So the 0 again gets inverted one time, and S is equal to 1. And let's go ahead and jump down to this next case, not the next case, but let's skip over the next case and go to this one. When C is 1 and X and Y are both 0. Again, we will get 1 for S, because the 1 value for C causes an inversion here, and since X and Y are both 0, we have no inversions there. So that's still one more case where we have one inversion, and so the 0 goes to 1 to give us S is equal to 1. So that's all the cases, and I think that from the way we discussed that, you can see that when if we look at C and X and Y, if an odd number of those three, there's three variables there, C, X, and Y. If an odd number of them is equal to 1, then this 0 will be inverted an odd number of times, and S will be equal to 1. But on the other hand, if an even number of these is equal to 1, then the 0 will be inverted an even number of times, and S will be equal to 0. So if we go back up to this case now, here we have 2 of C, X, and Y. 2 of those values are equal to 1. And so we have an even number of inversions, and S will be equal to 0. And let's make sure we understand. Okay, here's 0 coming in on this line. Since C is equal to 0, it doesn't get inverted there. But since X is equal to 1, it gets inverted to become 1 there. But then since Y is equal to 1, that 1 that's here will get inverted again back to 0, and so S will be 0. And likewise, when we come down here to this line, we have, again, an even number of 1s here. We have 2 1s in that row, so again, S will be 0. And in the next to last line, again, we have an even number of 1s, and so S will be 0. But in the final line, we have an odd number of 1s, and so that means that this 0 will get inverted once, twice, 3 times, and so S will be equal to 1. Now let's look at the more complicated of these two, which is C prime. And let's just go case by case. So when C and X and Y are all 0, let's see, okay, here is the C prime line right here. So the fact that X and Y are both 0 will cause an inversion here. The fact that C and X are both 0 will cause an inversion here. And the fact that C and Y are both 0 will cause an inversion here. So there are 3 inversions of 0, and so C prime will be 1. I'm sorry. Let's do that again. Obviously, the way that the Toffoli Gate works is not if if both of the inputs are 0, but it activates when both of the inputs are 1. So the fact that both of these are 0 means nothing happens here. The fact that both of these are 0 means that nothing happens down here. And the fact that both of these are 0 means that nothing happens here. And therefore, C prime, this 0 goes straight through to give us C prime is equal to 0. Sorry about that. Okay. Now, for the next line, when C and X are both 0 and Y is equal to 1, well, in fact, I guess we can go ahead and reason very quickly. For C prime, since it's controlled entirely by Toffoli gates, and Toffoli gates require at least 2, all 3 of these Toffoli gates will require at least 2 of the 3 variables Cx and Y to be 1, then whenever we have just one of those equal to 1, this 0 is going to go all the way through and C prime will be 0. So in this next case, we only have 1, 1, so then C prime will be 0. In the next case, again, only one of those is equal to 1, so C prime will be 0. Now in the next case, C is 0, but X and Y are both 1. So this Toffoli gate will not do anything since we have C is 0 and X is 1. This one will not do anything since C is 0 and Y is 1. But this one will cause an inversion because X and Y are both 1. So this 0 will get inverted one time to give us C prime equals 1. Now we're back in the next line to a case where only one of the 3 variables is equal to 1, so C prime will be 0. Here, in this case, 2 of them are equal to 1, so we look, we do have here C and Y. They're both equal to 1, so this one will cause an inversion, but since X is equal to 0, this one will not cause an inversion, and this one will not cause an inversion. So we have just one inversion occurring, and so 0 becomes 1, and C prime will be 1 in this case. And likewise in this case, C and X are both 1, but Y is 0. So this one will this Toffoli gate will cause an inversion, but this one will not, and this one will not, because for both of those it depends on Y, and Y is equal to 0. So we have only one inversion here, 0 becomes 1, so C prime is 1. And then finally, when C and X and Y are all equal to 1, then each one of these Toffoli gates will cause an inversion. So there are 3 inversions of 0, so 0 goes to 1, goes to 0, and then to 1. So C prime is equal to 1. And now we stand back and ask ourselves if we can recognize what this circuit is doing. And I claim that this is a 1-bit full adder, where C prime is the carry-in bit, C prime is carry out, and S is the sum bit. And if we go through the cases, you can see that this is exactly right. If we have 0 and 0 and 0, we get 0 with a carry of 0. 0, 0, 1 is 1 with a carry of 0. 0, 1, 0 is 1 with a carry of 0. 0, 1, and 1, that gives us 2, which of course in binary is 1, 0. So we get a sum of 0 and a carry of 1. 1 and 0 is 0 is 1 with a carry of 0. 1 and 0 and 1 is 2, so that's 0, carry 1. 1 and 1 and 0 is 2, so that's 0, carry 1. And finally 1 and 1 and 1 is 3, so that's 1, carry 1. And so indeed, this is a 1-bit full adder. And it just is an example of how Toffoli gates and controlled NOT gates can be used to realize a more complicated circuit. So now let's look at some problems. Okay, so I have a couple of easy questions for you here, and both of them concern the Toffoli Gate. So let's read the introduction here to the problems. The Toffoli Gate has 3 inputs and 3 outputs, each of which can assume the values 0 or 1. So its matrix has dimensions 8 by 8. Let M be the matrix representation of the Toffoli Gate relative to the standard basis. And that's 0, 0 in this order: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now let me make sure you understand. There's a couple of things going on here that I want to make sure you're aware of. Okay, with each one of these kets, we're thinking of the first qubit as being the entry. Let's look up here with our Toffoli Gate. So the first qubit in the ket is going in this first line. The second qubit is going in the second line, and the third qubit is going in the third line. For each one of these, you see that each one of these is a 3-qubit ket here. So again, the first qubit goes in that first line of the Toffoli Gate. The second qubit goes in the second line of the Toffoli Gate, and the third qubit goes in the third line of the Toffoli Gate. Now, so that's one thing you need to be aware of, and of course that's true for all of these kets. And then the second thing you need to be aware of is that this ordering implies that we're thinking of 0, 0, 0 being represented by the column vector 1 and then 7 zeros. 0, 0, 1 is represented by the column vector 0, 1 and then 6 zeros. Then this would be 0, 0, 1, 5 zeros, 0, 0, 0, 1 and 4 zeros, and so on. Or another way of putting it is that the image, what the Toffoli Gate does to 0, 0, 0 will appear in the first column of M. What the Toffoli Gate does to 0, 0, 1 will be in the second column of M. What it does to 0, 1, 0 will be in the third column of M, and so on. Now, I don't want to give too much away, but so I'll stop there. But you should see from this description that I've just given, you should see that the first 6 columns of M are all zeros except for a 1 in the diagonal. So each of those first 6 columns will have a 1 in its diagonal element and a 0 everywhere else. That's for the first 6 columns. And the questions concern columns 7 and 8. And the questions are simple. The 25.1 says, in what row or rows do non-zero terms appear in the 7th column, and what values appear there? So you'll have, if you think that there's just one non-zero row in M in column 7, if you think only one non-zero term appears in column 7, then you'll have 2 answers here. One will be the row in which it appears, in which the non-zero term appears, and then the second answer will be the value of that non-zero term. On the other hand, if you think that non-zero terms appear in 2 rows, then you'll give me a row and a number, and then another row and another number. So just make sure that you tell me here in what rows there are non-zero terms, and make sure it's clear what non-zero terms appear in those rows that you identify. And you're going to do that for the 7th column and also do that for the 8th column. And those will be the 2 at-home questions for Lecture 25. And then we'll also have at least 1 in-class problem for Lecture 25. And that's it. That concludes Lecture 25. So good luck.